Welcome back to another Forge College Explainer. So in our last session together, we hammered out the final security audit checklist for an EVM to SVM migration. We got really good at spotting classic EVM vulnerabilities, things like reentrancy or unchecked math, and mapped out exactly how those translate into Solana pitfalls. Well, today, we're zooming out. We are taking that granular knowledge and applying it to your overarching architecture. Because look, moving an entire smart contract from Ethereum to Solana, it's a massive undertaking. We're not just copying and pasting code here, we're translating economic and security intents. Think of it like moving to a new house. Sure, moving your stuff is hard, but moving the entire foundation of the house to a completely different climate, that requires a totally new set of blueprints. So let's jump right in and sketch out exactly why porting smart contracts matters, and more importantly, how to do it right.
All right, here is our architectural blueprint for today. We'll be hitting why port smart contracts, the great mental shift, identifying migration risks, auditing your dependencies, the migration master plan, and finally, our conclusion and next steps.
Okay, Section 1, why port smart contracts? Let's talk about the real motivations driving this.
Usually porting a working EVM project over to a native Solana implementation is driven by some pretty heavy business goals. You're after faster execution, dramatically lower fees, or maybe you just want to tap into a completely new liquidity ecosystem. But to actually pull that off, you can't just take Solidity logic and violently shove it into a Rust compiler. It doesn't work that way. What you're really moving is what we call the contract surface. Imagine this as the literal footprint of your house. It's your external entry points, your persistent state items, and all those cross-contract integrations. Your primary goal here is to redesign that exact surface while absolutely guaranteeing that the economic and security constraints, who can do what and what is strictly forbidden, remain 100% intact.
Moving on to Section 2, the great mental shift, we are going from implicit to explicit.
Now this right here is honestly the biggest foundational shift of your entire migration journey. To put it simply, the EVM is basically your overly trusting roommate who leaves their wallet sitting out on the kitchen counter and relies heavily on implicit callers like msg.sender and global storage mappings that just sort of exist in the background environment. Solana is like a strict, no-nonsense bank teller. It demands explicit signers. It's checking IDs for every single transaction, and it absolutely requires you to pass in exact, predefined account structures if you want to mutate any state. On Solana, there's no pulling variables out of thin air. You're moving away from environmental assumptions and stepping into a world of explicit account-based state and explicit observability.
And to handle this massive shift in how we map state, we rely on something called a PDA, or a program-derived address. In the EVM, you're probably used to tossing user balances into a global mapping stored directly inside the program. Well, on Solana, you can't just mutate global mappings like that. Instead, you map each account's specific data to a PDA. What is it? It's simply an account whose address is deterministically derived from your program ID combined with specific seeds. It's an absolutely crucial concept to grasp because it is exactly how those implicit floating EVM mappings get translated into Solana's explicit, highly secure account-based state.
Section 3. Identifying migration risks. Time to look for structural cracks.
Before we even think about building the walls of our new application, we have to aggressively stress test our framework. We're looking for anything that might break our functionality, and we usually categorize these into 3 core risks. First up, behavioral risks. These are those sneaky, unintended changes to your contract semantics. Think about an execution path silently changing just because a require statement wasn't properly translated into a Solana runtime error. Second, we have structural risks. These are the massive, sweeping shifts in how your state is laid out or fundamental changes to the account model itself. And third, dependency risks. These pop up when you rely on external libraries or contracts that simply might not exist over in the Solana ecosystem.
Now, listen closely, because this is the crucial takeaway. Structural risks are, by far, the most dangerous of the bunch. They demand your immediate attention. You will have to re-architect your storage layout or split your functionality across multiple accounts right out of the gate. These have to be tackled first during your mapping phase. If you brush structural risks off until later in the dev cycle, you might literally find yourself tearing down the house after you've already built it, simply because the foundation can't hold your data.
Section 4. Auditing your dependencies. Let's see what's hiding in your imports.
Dependency risks love to hide deep down inside your imported libraries. So let's look at some concrete examples of how you'd handle them. Say you're using OpenZeppelin's Ownable and Solidity. Cool, but on Solana, you have to actively make a choice.
Are you mapping ownership to a PDA, or are you going to use a multisig via a completely separate program? Or what about safe math? Look, bringing EVM's safe math over to Rust is literally like bringing a horse to a Formula One race. It's totally unnecessary because Rust already has checked math built right in with checked add and checked sub. And if your Ethereum setup relies on an inline Oracle interface executing in the same transaction, on Solana, you're almost certainly going to be reading an off-chain data feed from a separate account. Every single dependency forces a conscious design choice.
Okay, massive warning light flashing on the dashboard right now. Inline EVM opcodes and assembly, they have absolutely zero direct translation on Solana. None whatsoever. If you are auditing your dependencies and you spot a library leaning on these, you are staring down a medium to high risk situation. That logic has to be completely torn down, reimagined, and rebuilt from scratch in Rust. You need to plan for that reality incredibly early in your timeline.
Section 5. The Migration Master Plan. So with all our risks clearly identified, how do we actually guarantee a secure build and avoid that nightmare scenario of tearing it all down? We use a strict 5-stage workflow. Stage 1 is discovery and inventory, literally listing out everything on your contract surface. Stage 2 is risk classification, tagging all those structural, behavioral, and dependency risks we just talked about. Stage 3 is building a prototype port, just taking a tiny, critical slice of functionality and moving it over. Stage 4 is integration testing, making sure cross-account atomicity actually works. And finally, Stage 5 is your rollout plan, your upgrade strategies and staging environments. This whole flow is designed to separate your early discovery phase from making irreversible, permanent storage choices.
To keep everybody on the same page, you want a tight planning matrix. Engineering takes the lead on extracting the contract surface into a simple CSV file. Your security team owns the risk classification, which gives you a well-documented risk matrix. And then engineering steps back in to own the prototype port, delivering a bare-bones, minimal anchor program. I seriously cannot overstate this. Forcing yourselves to build a small, testable prototype early on is going to save you from incredibly expensive rework later when the launch deadlines are looming. It's just common sense, right? Test the foundation before you buy all the heavy furniture.
Section 6. Conclusion and next steps. Let's wrap this up.
If you remember absolutely nothing else from this explainer today, please let it be this quote. Preserve intent, make state explicit, and prototype early. That right there is your golden rule. Burn those 3 principles into your brain. Focus on keeping your economic invariant identical, convert that sloppy implicit global storage into tight explicit account level state, and always prototype a minimal slice of your critical functions first so those structural changes reveal themselves instantly. So what's next? In our very next lesson, we are going to dive straight into mapping the contract surface for porting. I need you to go back and grab all those specific artifacts you generated from our previous security module, bring your entry point maps, pull up your state diagrams, and have those annotated dependency lists ready to go. We are going to use those exact documents to draw up a precise surface map that will act as the blueprint for your actual code transformations. So the final question I have for you is, are you ready to map out your contract's completely new foundation? I really hope this explainer gave you the structural clarity you need to tackle this migration safely and effectively. To dive deeper into the subject, explore more Web3 topics, and continue along this track, make sure to visit our website at forge.college. This explainer was brought to you by Forge College. I'm your host, and I will see you in the mapping phase.